I would like to call on our next speaker. Our next speaker is Theodore Borromeo Achacoso. I always go slow because I might mispronounce it. So Dr. Theodore Borromeo Achacoso was a college graduate in BS Biology at the age of 18 and a Doctor of Medicine at the age of 22. Post-medically, he trained, he researched, and worked in many different fields. For one, in interventional neuroradiology and pharmacology in Manila. Two, in medical informatics and artificial intelligence in Washington, D.C. Three, as a scientific advisor to local venture and global institutional investment funds in Bethesda, Maryland. Four, as founder and chief technology officer of a group communication and collaboration software company in Rosslyn, Virginia. Five, as quant and trader for an incubator hedge fund in Rehoboth Beach, Delaware. Six, in anti-aging medicine and nutritional medicine in Paris, Brussels, Monte Carlo. He's all over the world. Now, his representative body of work includes a book containing the first ever neural circuitry database for an organism, journal articles, US patents, software, grants and recorded interviews, webcasts, and speaking engagements in the areas of one, artificial ethology, look it up, it is the study of human behavior from biological perspective, computational neuroethology, biomathematical modeling of nervous systems, and computability of consciousness. Two, on medical informatics, medical decision-making, correctionist systems, and expert systems. Three, computer-assisted imaging, edge detection algorithms, and telehealth. Four, virtual group dynamics, communications, and collaboration methods. Five, parallel cluster, cloud, and distributed emergent computing. And six, predictive complex adaptive system modeling of financial time series. Based in Washington, D.C. and keeping ties in Europe, Dr. Achacoso has established a telemedicine practice in anti-aging medicine and in nutritional medicine in Manila, where he is a co-founder and chief science officer of the BioBalance Wellness Institute. His IQ registers at 186, and thus this mess, according to him. Well, this doesn't look like a mess to me. This is totally impressive, and it is my honor to introduce to you, I haven't met him, Dr. Theodore Borromeo Achacoso. Yes, sir. Pleased to meet you, sir.
Everybody stand up. You have a postprandial dip. Please stand up and reach up as high as you can and breathe 5 times. And 1, on your tippy toes. 1, 2, 3, 4, 5. They said, you can sit down now. They said that evolutionarily one of the things that we have lost is reaching out for fruits, right? So we have very poor shoulder girdles as we wake up. As we grow older. All right, she's 47 years old, and she certainly can wash my kitchen floor anytime. As a reminder to everyone, this is a variant of a lecture in continuing medical education. I've started a series of lectures called Continuing Basic Medical Education, which serves to refresh your knowledge of basic medical education, medical information, update, and change the information that we have learned from medical school, because a lot has changed since that time. All right. Since I'm only here 30 days every quarter, and I'm elsewhere all the time, people said that I should say something personal about myself. Well, I try to remain imaginative because, as Einstein said, knowledge has its limits. I am more curious than imaginative, and All of the interventions that I am going to introduce here for you to learn, I have already tried on myself, except for estrogen, but I am still alive. All right, so let's see where my curiosity led me. In 2011, there was a film called Limitless, right? With a colorless pill that you take it and your mind becomes limitless. Well, in June 28 of this year, I found this study that methylene blue shows promise for improving short-term memory in humans. And so maybe it's not a colorless pill, so I made myself a blue gum. Well, it works, and as soon as I remove the bitterness from the gum, I'll share it all with you. Now, my next curiosity is what came out last year in Wired magazine. He says, end of life as you know it, the Genesis engine, editing DNA is now as easy as cut and paste. Welcome to the post-natural world. And the genetic breakthrough that could change humanity. Wouldn't that make you curious? And of course, perfect humans and designer babies, how CRISPR technology edits genes in the human DNA. So what did I do? Where did my curiosity lead me? I bought an entire laboratory for CRISPR-Cas gene editing, and I'm transforming my 4th floor bathroom into a gene editing laboratory. Sorry guys, I know some of you have PhDs in genetic engineering here. They are now high school science projects. Now, let me see whether or not I could get you interested and curious enough about molecular inflammation so that you guys can do something about it, right? So, what is classical inflammation? We know from medical school, acute inflammation generally looks like this. You have a thorn, it pricks you, you introduce some bacteria, your cells come in and defend you, and the major players in the response are what cells? They are the neutrophils, right? Feel free to answer aloud if you know the answer. All right, in chronic inflammation looks like this. Here in the Philippines, we usually represent this with a caseation granuloma from tuberculosis. But a reminder, I know there are surgeons here, if you leave sutures that don't dissolve, then you have your granuloma, suture granuloma. And the major responders here are what cells? They are your macrophages, right? But what about molecular inflammation? How does molecular inflammation look like? I know your imagination is running wild, but molecular inflammation looks like this. Obesity, heart disease, lipid problems, hypertension, type 2 diabetes, dementia, cancer, PCOS, and non-alcoholic fatty liver disease. Now, the major players here are the responses to chronic redox imbalance. All right. Now, so classical inflammation is of 2 types. You have acute inflammation and chronic inflammation. We've been looking at slides, so we know that the basic definition comes from pathology, and the clinical practice comes from infectious diseases, like your acute infections, immunology, like your asthma, and surgery, for example, like in your acute appendicitis. Now, molecular inflammation is also known as meta-inflammation, metabolic inflammation, inflammaging, chronic systemic inflammation, and cold inflammation. The basic definition comes from molecular biology, and the clinical practice is in health optimization medicine, which I have started as a specialty. Now, the discovery pattern for vitamin D, when we were taught in medical school, is that 100% of the activation of vitamin D occurred in the kidneys, and then vitamin D exerted its calcium metabolic effects, right? But we now know that's only 15% of the pathway. That's the old pathway, and the new pathway says vitamin D can be activated by virtually all nucleated cells in the body, and that accounts for 85% of the other activation. Now, this discovery pattern is what I applied. This discovery pattern is uniquely mine. It's the first time that you're hearing about it in any lecture. It's the same discovery pattern as for molecular inflammation. So the old classical inflammation, acute and chronic, only immune cells can be activated to produce pro-inflammatory and anti-inflammatory molecules in response to pathogens or physical chemical agents. The new molecular inflammation, virtually all nucleated cells can be activated to produce pro-inflammatory and anti-inflammatory molecules in response to redox imbalance. Now, if this is the only thing that you take away from this lecture, I'd be very happy. All right, so what is molecular inflammation at the molecular level? In order to do this, I have to give you a crash course in cell signaling. You all know this from medical school, so don't pretend that this is complex. Actually, take a look at the right-hand side of the screen, and it only consists of 4 parts, really. The input, the red dots here are the input. The input can be intracellular, extracellular, and then there's processing via intracellular signaling proteins. Now, if you want to sound really sophisticated, you say, instead of processing, say signal transduction. And then from processing, you have your output by effector proteins, and then your responses. So input, processing, or signal transduction, output, and responses. That's the major pathway. We all learned that from medical school. Now, for this particular lecture, I would like to touch on one particular input, which is intracellular, which is the reactive species, especially the reactive oxygen species, or ROS, and 2 transcription factors, NF-kappa B and Nrf2. Now, the intracellular signaling proteins can enter the nucleus in order to activate or turn on certain genes to produce certain proteins. And so those are called transcription factors. You know, it's not a scary term because, you know, the DNA is transcribed and then translated. So transcription factor simply means a switch to turn on and off certain genes. And for this lecture, it's NF-kappa B and Nrf2. Now, pulling away from that picture, that's actually a slow response of the body to defend itself. All right, so on the right-hand side, that's the slow. It takes minutes to hours where you actually have transcription and translation to proteins. The fast will not require any transcription or translation. It just produces altered protein function, and the cell can defend itself. So the fast is less than a second to minutes. And as I said, we're going to take up ROS as the input molecule here, and the transcription factor is NF-kappa B and Nrf2 in the slow pathway. All right, this is a close-up of the transcription regulators. As the horizontal gray line is your DNA, and this is where your transcription factors would bind to activate certain genes, like your NF-kappa B and Nrf2. Now, this is the most difficult slide, so bear with me. It's difficult only because you have to recall your biochemistry. There are biochemistry professors here, and they will be paying attention because they will be giving these exams to their medical students. Now, take a look at oxygen. Just follow the red arrow. There's oxygen right there. It gets converted to superoxide radical, or the singlet radical. Here it's shown by 4 mechanisms. Xanthine oxidase, for example, is used as it produces a lot of superoxide radicals. And the anti-gout medication that you use to inhibit xanthine oxidase is what? Allopurinol, right? So in pain management protocols that you see these days in patients without gout, you may see xanthine oxidase in there that is actually to decrease the superoxide radical. Now, there's also NADPH oxidase, which produces a lot of superoxide radicals. This is used in the FAST pathway. It produces a lot of superoxide radicals in order to kill viruses and bacteria in what's called the respiratory burst response of the cell, right? Cardiologists here probably puking iNOS. It's been in the newspapers and the journals for so many years. That's endothelial nitric oxide synthase. And of course, most famous for producing ROS is the electron transport chain of the mitochondria. Now, the singlet oxygen is then dismutated by superoxide dismutase into hydrogen peroxide. Now, what element is associated with the superoxide dismutase in the mitochondrial matrix? It is manganese, right? So it's manganese superoxide dismutase. And in the cytosol, the superoxide dismutase is copper zinc superoxide dismutase. It's also in the intermembrane space of the mitochondria. Now, if you take a look here, the dismutation is actually quite slow. And if you have nitric oxide in there, it's 3 to 4 times converted to peroxynitrite. All right, which is another reactive species called the reactive nitrogen species. We won't be talking about that in this lecture. Now, from hydrogen peroxide is then detoxified into water by your glutathione peroxidase, right? And then, of course, you have your peroxyredoxins and thioredoxins. Peroxyredoxins can act alone, but your thioredoxins need your peroxyredoxins to convert hydrogen peroxide to water. And then there's catalase, which converts hydrogen peroxide to water and oxygen. And then, of course, here's a very famous Fenton reaction, which biochemists love to give in their exams to medical students in medical school. And this is significant because it's in the presence of iron, and the hydroxyl free radical is the only free radical in the body for which the body has no defense. All right, the lifespan of a hydroxyl free radical is very short. It's in femtoseconds, but in the process of killing viruses and bacteria, it can also damage your DNA and your cell membranes. And then, of course, there's an enzyme called myeloperoxidase, or MPO, which produces hypochlorous acid. Now, a professor of mine in nutritional medicine used to love to answer this question: what's the only amino acid that can neutralize hypochlorous acid? It's actually taurine. That's why in MI patients, in order to mitigate the damage from myocardial infarction, they are now trying to infuse taurine into the patients because of the damage done by hypochlorous acid. All right. Now, as we said, we are going to review quickly the electron transport chain. It's actually very simple. There are 4 complexes, complex 1, 2, 3, and 4. And it's complex 1 that actually gives off a superoxide radical. Now, just look closely, as complex 1 actually is flavin mononucleotide. So flavin, as in riboflavin, so now you know why vitamin B2 is important. And then, of course, it's iron-sulfur clusters. Your iron and sulfur, when you remember them, they're only relevant to you in terms of hemoglobin, but really, hemoglobin starts where? Where's the genesis of hemoglobin? It starts with the mitochondria. All right, the other complex that provides superoxide radicals is complex 3. And again, if you look closely, it uses iron and sulfur. And just for your education, if you look at complex 4, that's where copper is actually used by the body. So this is the significance of the trace minerals that you're eating or taking in as supplements. Now, let's take a look at the darn endothelial nitric oxide synthase. There is a cofactor which we used to ignore in medical school. It's tetrahydrobiopterin, or BH4. It's very difficult to synthesize, but it's now available as a supplement. Now, as we said earlier, the production of peroxynitrite is actually faster than you can dismutate the superoxide ion, and you can actually oxidize your tetrahydrobiopterin. And then what happens is that the enzyme, endothelial nitric oxide synthase, will start producing your singlet oxygen. All right, so that's the most difficult part. Now we're done. Here, this is very simple. The yellow part is the mitochondrion. As you can take a look, there's follow the circle. That's a hydrogen peroxide there is inside. The manganese superoxide dismutase actually converts a singlet oxygen into hydrogen peroxide, and then it migrates outside the cell and is actually used by the cell for redox signaling. So not all superoxide radicals are bad, because another way of looking at it is that at low levels or at normal levels, they are used by the body for redox signaling. Otherwise, if there's too much, you have mitochondrial dysfunction, disease, and aging. All right, this is a simpler way of looking at it. You have to balance your ROS in order to have proper stem cell renewal, proliferation, and differentiation, healthy immune response, and longevity. Otherwise, you'll have senescence, autoimmunity, tumorigenesis, and stem cell exhaustion. All right. Now that we've finished the reactive oxygen species input, let's now take the pro-inflammatory transcription factor NF-kappa B. It's a master regulatory transcription factor for the inflammatory processes in the body. All right, it looks like this. NF-kappa B actually is just responsible for our inflammatory immunity, and it produces things like cytokines, chemokines, cytokine immune receptors, and so on. What's bad about it is that NF-kappa B is both activated by and induces the expression of inflammatory cytokines in the loop. So the more you have the genes activated to produce inflammatory cytokines, the more the NF-kappa B will get activated. It is also anti-apoptotic and activates the proliferation genes, and it is heavily implicated in the genesis of cancers. So this is just a list for you to quickly peruse. What are the target genes? What does it turn on? Okay, cytokines, immunoreceptors, so anything that actually increases the inflammation of the body, including even turning on some of the viral DNA. So here's a sample of the cytokines that it produces, or the molecules that it produces. On the left-hand side, you could take a look at the inflammatory cytokines like TNF-alpha, interleukin-1 alpha, IL-1B, IL-6, IL-10, COX-2, which is implicated in pain. And then on the right-hand side, you take a look at metabolism, and below you see a decrease in the expression of mitochondrial genes that are actually coming in from the nucleus. So you have less mitochondrial biogenesis and therefore less energy for your patients to heal. Now, so this is the slide where I'd like you to work with me. You have overexpression of NF-kappa B, and you have bone resorption, atherosclerosis, heart failure, cancers, COPD, diabetes, sepsis, and so on. So why don't you work with me in actually down-regulating NF-kappa B, and I'll teach you how to do this later on. When your patients already have diseases, it also behooves you to actually decrease the activity of your NF-kappa B. Now, if there is a master inflammatory switch, there is a master anti-inflammatory switch. It's called the NRF2. Now, it looks like this. There's oxidative stress. It activates the NRF2. NRF2 migrates to the nucleus as a transcription factor. It binds to the antioxidant response elements, and both of them use polymerase 2 to generate glutathione, eliminate ROS, detoxify, excrete drugs, and synthesize NADPH. Now, these are some of the target genes. The genes for the direct antioxidants, for increased levels of GSH synthesis, for the stimulation of NADPH synthesis, and increased detoxification of hydrogen peroxide, penoxynitrite, and hypochlorous acid. All right, this is just a sample of the genes that are activated. As you can see, these are all anti-inflammatory genes: anti-NADPH production, iron sequestration, glutathione utilization, quinone detoxification, glutathione production, and thioredoxin production. Everything that is anti-inflammatory. So I would like you guys to work with me. This is a healthy lung, skin, liver, brain, GI tract, kidney, spleen, erythrocyte, retinal epithelia. I know there's an ophthalmologist here. So even before, to keep your organs healthy, why don't you work with me in upregulating the NRF2 transcription factors in the bodies of your patients? All right, so this is classic inflammation signaling. As we said earlier, it's two pathways. And this is actually very easy. Don't get cowed by it. This is the input, pathogens. In the last 10 years, you probably have been over-inundated with PAMPs and DAMPs, pathogen-associated molecular patterns and danger-associated molecular patterns. These are simply inputs. And then, of course, the most famous receptors in your immune cells are the TLRs, or your toll-like receptors. You should be reading this in all the journals by now, guys. This is just a review. All right? And then it, of course, turns on your NF-kappa B, which then enters your nucleus and then synthesizes your inflammatory cytokines. All right? And that is the slow pathway. But what about the fast pathway? There's a danger-associated molecular patterns as input, and then, of course, your most famous intracellular receptor are the node-like receptors, or the NLRs, and the most famous of which is the P3. And it binds with procaspase 1 and cleaves it to caspase, and of course activates other inflammatory cytokines contributing to the systemic inflammatory response. Now, the reason why I put this slide in is for you probably have heard of the word inflammasome. And inflammasomes have just been elucidated in the past few years. And I'm a sucker for beauty, and these things are very, very beautiful molecules if you get to see them. All right. classical inflammation, I know you guys do know this. This is very, very simple because I do remember from immunology the term diapedesis, right? So, but before diapedesis happens, there is rolling, activation, adhesion, crawling, and transendothelial migration of your white blood cells. All right, the reason for this slide is actually on the left-hand side. If you see things such as selectins, integrins, or immunoglobulins that end in AM, AM stands for adhesion molecules. And that's the only reason why you should be familiar with these terms. All right, so classical inflammation, of course, the pain, you have increased blood flow, you have fluid release into tissues, there's extravasation of leukocytes to the site of injury, there's fever and proliferation of leukocytes, there's heat, redness, swelling, tenderness, and pain. All right, so molecular inflammation, this is the signaling. You could see that oxidative stress would actually activate your NF-kappa B because your body has to fight off via inflammation. But at the same time, your body will start activating your Nrf2 transcription factor, producing your antioxidant and cytoprotective molecules. So they come in a balance. When they come out of balance, when you have too much oxidative stress, your body won't be able to cope with the stress, and therefore you have molecular inflammation. So where is the pain in molecular inflammation? Reactive oxygen species actually sensitizes the peripheral nociceptors, and it also sensitizes the central dorsal horn neurons, causing persistent pain. Not only that, ROS is not the only thing that can cause you pain. Even cytokines can actually cause peripheral sensitization of your nociceptors and a central sensitization of your dorsal horn neurons, causing pain. So this is a summary of molecular inflammation. In normal healing, you have a stimulus, the body fights it, and then you have your healing. If there's an ongoing stimulus, say a very high level of oxidative stress, then you have a repetitive cycle causing disease. Now, this is in your handouts. This is how it's represented. So you have your redox imbalance, and then there's your signal transduction pathway or signaling kinases. Upregulation of your NF-kappa B causing increased pro-inflammatory molecules, your cytokines, your adhesion molecules, your inducible nitric oxide synthase, your COX-2, which is implicated in pain. And then there's tissue damage and chronic inflammation, and this is a feedback loop to produce more reactive species, and you have aging, age-related diseases and pain. All right, so here's your balance. You can see that the pro-inflammatory is heavy, TNF-alpha, IL-1 beta, IL-8, IL-12, interferon gamma. These are all pro-inflammatory, and you're light on your anti-inflammatory cytokines. All right, so how is molecular inflammation the common pathway for aging, chronic diseases, and their attendant pain? We're done with the molecular stuff. This is easier. All right, so we have to review again your cell signaling responses. As we said on the right-hand side, it's very simple. There's input, processing, output, and response. And we have taken up the input signal, reactive oxygen species. We have taken up the two transcription factors in the slow pathway, NF-kappa B and Nrf2. And then now, let's take a look at the responses: altered metabolism, altered gene expression, and altered cell shape or movement. Now, there are two types of macrophages. M1 is the pro-inflammatory macrophage, and M2 is the anti-inflammatory macrophage. And as you can see here, and you can guess, in a pro-inflammatory macrophage, the NF-kappa B is upregulated. In an M2 macrophage, an anti-inflammatory macrophage, the NF-kappa B is downregulated. And what is not shown here is that in an anti-inflammatory macrophage, your Nrf2 is upregulated. All right. So this is a very simple slide showing the central pathway. You have your macrophage actually going only to two types of cells: the epithelial cell and the mesenchymal cell. So epithelial cells such as the endothelial cell, the enterocyte, the glomerular enterocyte, and the bronchoalveolar cells. And then for the mesenchymal cells, you have the smooth muscle cells, fibroblasts, myofibroblasts, synoviocytes, and mesangial cells, which are found where? Are mesangial cells found? Oh, come on, your pathology professors will kill you. They're found in the kidneys. All right, so let's play a quick game here. Macrophages, where they are found, are called by different names. When they are found in the brain, they are called microglia. Where they're found in the lung, they are called alveolar macrophages, of course. They're found in the liver. What are they called? Kupffer cells. Very good. And when they're found still in the bloodstream, they have not become macrophages yet. They are called what? Monocytes, right? And then when they're found in the spleen and in the lymph nodes, they are called what? Sinus histiocytes. Ah, forgotten already. Basic pathology. All right. Now, this is the core slide of this segment. We'll take, as an example, your adipose tissue. Okay, in the lean adipose tissue, you have a preponderance of your M2 macrophages, which are anti-inflammatory, and they're represented here as the green cells. All right, and then as you get more obese, you have an increased preponderance of your M1 macrophages, and more obese, there is already what's called a crowning around the adipocytes, and that's altered cell shape or movement. Okay. The second part is altered gene expression. As you can see, each cell has its own specific anti- and pro-inflammatory cytokines. For example, the anti-inflammatory adipokines like adiponectin, you know, in lean individuals. Whereas the pro-inflammatory adipokines, there is leptin, of course, your hunger hormone. The more you secrete this, the more you get hungry, right? So that's the altered gene expression. And then, of course, altered metabolism. As you become more obese, then you have loss of metabolic control. You always say metabolic control. What the hell is metabolic control? It is the loss of control of the anabolic and catabolic processes within your tissue, right? So now it looks like this. You have inactivity and obesity. That's why this is how molecular inflammation looks like. There's a chronic systemic inflammation, and if there's an upregulation of your NF-kappa B in your adipocytes, immune cells, and brain cells, then you get your insulin resistance and type 2 diabetes, your atherosclerosis, your Alzheimer's, Huntington's, and Parkinson's disease. And of course, there's an increase in local and systemic cytokines, and since it's pro-apoptotic, anti-apoptotic, then you have cancer. All right, so I'd like you guys to work with me to balance oxidative stress right at this level. You know, even if your patients already have the following diseases that are surrounding it. All right, so it's time to classify biological aging as a disease. Why? Because of this, the pink area is actually the mitochondrion. This is a very easy slide, just follow where the circle is. As you can see, right there is a decreased energy, increased ROS, altered redox regulation. And therefore, you have a progressive bioenergetic decline. And without any energy, you cannot heal, right? You cannot dispose of the garbage. You cannot regulate. You have cancers. You cannot provide energy to produce new muscle cells. You have sarcopenia. And so forth. So the degenerative disease, aging, metabolic disease, cancer, and immunologic disease. And this is the bioenergetic etiology of chronic diseases. Now, what can we do about molecular inflammation? It's the fun part. You are now experts in molecular and cellular portions of molecular inflammation. So I created a framework by which all of you can use in order to include health management in your disease management plans. You know, my slogan here is let's bring medicine home. So a very simple definition of health, which I give in all of my lectures, is that health is equal to A plus B plus C. Health is an optimal physiologic state characterized by A, the absence of disease, and B, the maintenance of balance between anabolism and catabolism, according to C, the cycle of life of the organism. So the absence of disease is illness medicine, what you guys are all practicing, and the balance between anabolism and catabolism is health optimization medicine. Now, just because you're not sick doesn't mean that you're well, it only means that you're not sick. Now, I have one major question, if you really understood my lecture so far. Is molecular inflammation anabolic or catabolic? Very good, it's anabolic. All right, so there's I created a quick health wrench for us to visualize health optimization medicine. So health is an optimal physiologic state characterized by the absence of disease, which is illness medicine. The types of medicine that we practice are several. We have allopathic medicine, alternative medicine, complementary medicine, integrative medicine, and functional medicine. And these all diagnose and treat disease. And let's flip it over to make it balanced. So we have to detect borderline deficiencies and subtle toxicities because they are not yet diseases when we try to balance the anabolic and catabolic processes according to the cycle of life of the organism, and that is called health optimization medicine, right? Illness medicine uses quantitative statistics. Of course, your drugs have to work across a population. Health optimization medicine uses qualitative statistics. Illness medicine uses evidence-based medicine or evidence-based illness medicine, and health optimization medicine uses evidence-informed, individualized care. This is the editorial of evidence-based medicine versus evidence-informed, individualized care, showing the rise and fall of evidence-based medicine and the rise of person-centered clinical medicine, which has found its home in Precision Medicine Initiative that was started last year in the United States, where now they prepare your chemotherapeutic cocktail depending on your single nucleotide polymorphisms that are found in your genes, whether or not you will respond to particular chemotherapeutic agent or not. So the treatment becomes highly individualized. So this is a quicker way of viewing it. In illness medicine, you guys do diagnose and treat diseases. Health optimization medicine, you detect and balance borderline deficiencies and subtle toxicities. You do disease management in illness medicine. We do health management in health optimization medicine. And you are concerned with lifespan, and in health optimization medicine, we are concerned with health span. All right, so this is the overarching program for health optimization medicine. All I want you to do is to add the detection of metabolic biomarkers in order for you to be able to do health management. All right, so you can then influence genetics, you can influence your symbionts, you can influence your environment, and you can influence your time in order to balance, say, the NRF2 and NF-kappa B transcription factors in your patients. So detection of early onset of metabolic regulations is the goal in health optimization medicine, and so we detect and balance the metabolome. Here you are detecting disease markers in illness medicine where you diagnose and treat diseases. Now, the sciences that are involved in health optimization medicine is very simple. To do the detection, we have the science of metabolomics or clinical metabolomics. It's been around for the past 20 years. It's become clinical in the last 5 years. Now, if you want to affect your genetics, then you use the science of epigenetics, such as manipulation through food, supplements, hormones, etc. And then if you want to manipulate your mitochondria, your endosymbionts, your mitochondria, and your exosymbionts, your gut microbiota, you use the sciences of bioenergetics and the gut immune system. If you want to manipulate your environment, then you use the science of exposomics, for example, the removal of toxins from your environment. And if you want to manipulate time, then you should learn about evolutionary medicine and chronobiology. So it's really very simple. You do the detection via metabolomics, and then you affect balance by influencing genes, symbionts, environment, and time. All right, so how do we detect ROS? How do we detect oxidative stress? You can do that. You can do that now. Take a look at the second line. You know, lipid peroxidases is the rusting of your cell membrane. And then the line after that is 8-hydroxydeoxyguanosine, which is the rusting of your DNA and is an early cancer marker. All right, so you can also detect mitochondrial function. Sorry guys, you used to memorize this, the Krebs, these are the metabolites of the Krebs cycle in medical school. Well, bad news, you have to memorize it again because we can detect it now. We can detect the levels. And why is it important? Because you know that when your mitochondria are not functioning properly, then you have the improper cofactors, improper levels of cofactors that are in there. And the most important cofactors in mitochondrial function are what? Vitamins B1, 2, 3, 5, alpha lipoic acid, and the mineral magnesium. All right. So you may want to check your essential fatty acids. Your essential fatty acids, like your omega-3s, can exert a modulating effect on your COX pathway, like your COX pathway and your 5-LOX pathway. And so why not check whether they need they need omega-3 before supplementing them. All right. So if there's if there's oxidative stress, is there an antioxidant-induced stress? Sure, there is. You know, many of you just take lots of vitamin C and lots of vitamin E. Of course, when you are scrubbing off the rust from something, something has to clean off that rust from someone else. So there's what's called an antioxidant regeneration pathway, where your antioxidant becomes oxidized itself, and then it becomes antioxidized by vitamin C, it becomes antioxidized by CoQ10, it gets antioxidized by your alpha-lipoic acid, and so forth. So what happens? If you raise your vitamin E levels, for example, a lot, then you will be able to sponge off a lot of the rust that's coming off from the cell, right? However, the others in the regeneration pathway, the levels are not increased, and so what? You have a stagnation of your vitamin E radical in there, which can then damage the cell further. So what do you do? So what I'm showing you now are the studies that, for example, the beta-carotene and retinal efficacy trial, like the CAROT trial of 18,000, at N of 18,000, they used vitamin A and carotene because of, it was stopped because of increased incidence of lung cancer and mortality. Alpha tocopherol, beta carotene, cancer prevention, 29,000 N, and alpha tocopherol and beta carotene, and increase again the mortality from lung cancer. Now you know why these are very poorly designed studies, because we know about the antioxidant regeneration pathway, and we never even considered this in the design of the studies. So now you know how to criticize studies like these. All right, so what do you do? Why don't you just measure? You can measure the antioxidant levels now. This ACE, CoQ10, and alpha-lipoic acid. This patient apparently needs also high levels of vitamin B1, B2, and B3. All right, you can also, the reason why I emphasized on magnesium, copper, zinc, and manganese a while ago is that you can now test for this intracellularly. These are not serum values. Okay, we can test intracellular levels of these to see whether or not your patient has sufficient levels of these. Now how do you detect imbalances in the NF-kappa B and NRF2? If there is any existing inflammation, then you should detect it. If your patient is allergic to any foods, then you should try to take them out of those foods. If your patient is actually has an inflamed gut, take a look at the second panel here. The calprotectin test is up. It means that your patient has inflammatory bowel disease. Your fecal secretory IgA, for example, is up, meaning your patient has a leaky gut syndrome. There was a time just a few years ago when leaky gut was not considered as a diagnosis, but now we know that microRNA 155 actually cleaves the tight junctions in your intestinal epithelium in order to provide that leak. And it's also been found in the brain, so there's also now a leaky brain syndrome. Now you could also take a look at toxins. You know, the second line from the top is MTBE, it's methyl tert butyl ether. This is usually from exposure to gas fumes, right? And then, of course, toxic elements like mercury. Mercury, the most common cause of this in patients is your amalgam fillings. All right, this is a beautiful slide. I was able to find it in a journal. It's NF-kappa B and Nrf2, the yin and yang of inflammatory response. So you only have three things to remember, really. Is one, you have to balance your reactive oxygen species. Then you have to downregulate your pro-inflammatory cytokines by downregulating NF-kappa B, and you have to upregulate your Nrf2. So how do we do that? So first strategy is to balance your ROS. I talked about taking care of your mitochondria. Then we should take care of the drugs that your patients are taking. Make sure you streamline the drugs because they are detoxified by the cytochrome P450 enzymes in the liver. So this throws off a lot of reactive oxygen species. So if someone in the group of the people who are taking care of your patients can please just streamline the drugs that your patients are taking, that will help a lot in decreasing molecular inflammation. And then, of course, removal of environmental toxins and removal of any inflammation in the body like allergies and inflammations in the gut. And of course, you measure and replace your antioxidants like vitamins A, C, E, lipoic acid, and coenzyme Q10. All right, now, the only significance of this slide is that it is 10 years old, and 10 years ago, there were already 785 downregulators of NF-kappa B. NF-kappa B was discovered first, and so there was a lot of studies done during that time. Now, you could see here that curcumin and resveratrol inhibit NF-kappa B mediated cytokine expression in adipocytes, and you have your COX-2 that is inhibited. Now, you see in cancer, the HIF-1 alpha, NF-kappa B, you could see that curcumin also downregulates the NF-kappa B. Okay, now how to upregulate NRF2? There are 4 known NRF2 activators: alpha-lipoic acid, TBHQ, sulforaphanes, and again resveratrol. And sulforaphanes produce the most potent effect. What are your sulforaphanes? Eat your broccoli, right? So here are the health-promoting factors that can upregulate your NRF2, many but not all phenolic antioxidants, your gamma and delta tocopherols and tocotrienols, but alpha tocopherol, which is the most common form of vitamin E, has very little activity. Isocyanates from broccoli, triterpenoids, sulfur from your garlic, right? And many carotenoids, fish oils, omega-3s, and of course exercise. So the traditional diets, like your traditional Mediterranean diet and traditional Okinawan diet, they work because they have the nutrient components of phenolic antioxidants, carotenoids, omega-3s, isothiocyanates, terpenoids, and garlic. All right, and NRF2 was discovered later than NF-kappa B, so the studies came out much later. So here is a summary of how to upregulate it. Your traditional Mediterranean Okinawan diets, a possible Paleolithic diet, and then the compounds that are in there: omega-3s, garlic, isothiocyanates, carotenoids, your tocopherols and tocotrienols. And then exercise, caloric restriction, can actually upregulate your NRF2. You have more antioxidant proteins, more mitochondrial biogenesis, increased lifespan and health span, and decreased chronic diseases of oxidative stress and inflammation. All right, and this is new from February of this year. We have lost certain foods from our diet that actually nourish certain bacteria like Lactobacillus plantarum, brevis, and collinoides, which produce catechols, and catechols upregulate your NRF2 pathway. So how do we then put it all together? So first, we use epigenetics, right? CR stands for caloric restriction, and this is in your handout, and you should, in your journal handout. Caloric restriction decreases your reactive species, and it only means that you should start eating less, right? And then you decrease your chronic inflammation and decrease aging and age-related diseases. You could also start exercising, right? Because it can inhibit molecular inflammation, but not too much. Then there's foods that fight inflammation. Of course, there's your broccoli. These are your dietary phytochemicals. But I know that many of you love to eat your fried food, sodas, refined carbs, lard, and processed meat, and those are highly inflammatory foods, right? And then, of course, to influence your epigenetics, you can use your supplements, like your curcumin, which can scavenge your free radicals. Okay, now it's time to take care of your symbionts. As you can see here, these are separate lectures in themselves. You should take care of decreasing the ROS in your mitochondria by taking care of your mitochondrial health, and of course, increasing your gut microbiota diversity so that you don't have increased cytokines that can lead to inflammation. And then taking care of your environment. If you take a look at the top, you know, UV light, ionizing radiation, air pollution, smoking. And if you look all the way to the bottom, there's cell death, age-related diseases, and aging acceleration. And then sleep. This was mentioned earlier. Sleep deprivation upregulates cytokines TNF-alpha, IL-1, IL-6, and CRP. If you have a patient that's sleep deprived, don't take the CRP levels the next day, right? Because the CRP levels will be high. So in summary, this is what we have. So you guys are working on both sides at the illness levels: Alzheimer's, Parkinson's, cardiovascular disease, COPD, diabetes, obesity, NFALD, nephritis, osteoarthritis, RA, osteoporosis, sarcopenia, and cancers, and you're using disease markers. Why not include test for your metabolic markers to detect oxidative stress and antioxidant-induced stress via metabolomics, and then reinstitute redox balance and by downregulating your NF-kappa B and upregulating your NRF2 via lifestyle modifications and custom dose bioactive and bioidentical molecules and substances. In fact, this can be generalized to include wellness in your clinical practice. You detect subtle toxicities and borderline deficiencies in the metabolome, push them back to optimal levels, and then you have a two-pronged approach to your patient. You have a disease management plan and a health management plan for your patients. But if you don't want to do your health management plan, I've been training health optimization medicine experts in this country. They're here. We can just refer them to us. Now, remember guys, that ain't your mama, no. Molecular information ain't your mama's swelling. Thank you.
Wow, that was a lot of information from Dr. Achacoso. Can we give Dr. Achacoso a big hand? Looks like I feel like I want to go back to medical school to review everything. But you know, it makes sense that Dr. Achacoso explained everything at a molecular level as the cause of almost all of the diseases. Doctor, I think we need your contact information for further questions.